So simply put, PES, it gives you these peaks, right? And these peaks tell you how many shells, how many subshells, and how many electrons are within those subshells. So that's what we're going to be reviewing, and then we'll do some problems. So I think it's just easiest to go with just with the elements. So let's start with hydrogen. If you guys remember, what is hydrogen's electron configuration?
1s.
1s. 1. Yeah. So this peak represents the one electron that is in the 1s subshell. Okay? Super simple. So let's go on to the next one. So helium, what's the electron configuration for helium?
1s2.
1s2. Good. So there are 2 electrons in the 1s subshell. And so same thing here, there is one peak because there's only one subshell. But if you look at the peak height, it's about double that of hydrogen, right? And so that shows that there are 2 electrons. Let's go to lithium next. The electron configuration for lithium is
1s2 p.
not
oh,
P.
Wait, 2p.
Not 2p.
Oh wait.
2. So if we look at the periodic table, lithium, and you guys should have your periodic tables out, by the way.
2s.
Yeah, it's 2s, and it's going to be 1. Good. All right, so make sure you have your periodic tables out. That way it's easy to look at. And so if you look at lithium right here, this first peak represents the 1s subshell. This second peak represents the 2s subshell. There are 2 electrons in the 1s subshell, and so it's going to be double the height of the 2s because there's twice as many electrons. All right, so we'll go on to beryllium now. If we take a look at beryllium, it's 1s2, 2s2, right? And so there are 4 electrons, and so we have 2 peaks. This one is the 1s subshell. This is the 2s subshell. And if you guys look, there's 2 peaks, and they're equal height because they have 2 electrons in each. Okay. All right, we'll move on to boron. Boron is where we change to 1s2, 2s2, 2p1. And so if you guys look, this peak is 1s. This peak right here is 2s. This one is 2p. Okay? And if you look at it, there are 2 electrons represented in this first peak, 2 here, and this is half the height of both of them, so that's going to be just 1 electron. Okay? So this is review, but any questions on this? Everybody good? All right. So now, before we're going to go into the practice problem now, but before we do, there is one thing I didn't mention last time, so we're going to add on to this PES. I want you guys to take a look at the x-axis, okay? And the x-axis is going to represent something called binding energy. Okay, so jot that down somewhere, binding energy. Okay, and binding energy, very simply put, is basically how tightly the atom holds the electron. Whoa. Okay, so how tightly the atom holds electrons. And it's specifically talking about within that subshell. Okay, so if you guys take a look, there are numbers right here. We'll talk about that in a sec. But these numbers represent the amount of energy it takes to remove electrons from that subshell. So you can kind of think of it as ionization energy for electrons in that specific subshell. Okay, so the binding energy is how tightly the atom holds the electron. Now, if you look at the numbers, what do you notice? Which side has the higher numbers, the left or the right? The left. Yeah, the left is 1,000 megajoules versus 0.1. So this right here represents you need more energy to remove electrons that are closer to the left. So basically, if you need more energy to remove it, electrons in the subshells on the left, they are held more tightly. So if you want to jot that down, in PES, subshells on the left are held more tightly. Okay, and that makes sense, right? Because the 1s is deeper into the atom than the 2s versus the 2p, so on and so forth. Okay. So that's the last part of PES that we did not talk about. It's about the x-axis. So as the peaks go are more to the left, the more tightly those electrons are held. Okay. All right, any questions on PES? That's pretty much all of it. We're not going to go into the other ones. Actually, I'll show you one more just so that we have a final idea before we go into the problem. But any general questions about the x-axis and whatnot? And again, this will be on your exam. I was looking at it yesterday, and you do have 1 or 2 PES questions, depending on your version. Okay, so let's go down a little bit more, just look at a little bit more complicated atoms. So we got silicon right here. And just for practice, let me give you guys a minute. I want you guys on your paper to write down the electron configuration for silicon. Just write down the electron configuration real quick. All right, guys, let's look at silicon and write the electron configuration. So silicon is right over here. So to get to silicon, we have 1s2. So 1s2. We have 2s2 right here. So 2s2. We have the 2p section that is filled up. So 2p6. And then we have 3s2 right here. And then lastly, we have 1, 2 in the 3p. So it'll be 3p2. Okay. So that is your electron configuration for silicon. And we can see that in the PES data. So if you take a look, this peak right here will represent 1s. This is 2s. Since they both have 2 electrons, equal height, 2p6 is right here. And since it's 6, it's going to be triple the height of these 2 peaks. And then right here, we have 3s, which is going to be the same as the other s and subshells. And then we have 3p2. So since there's 2, it's going to be the same as these other subshells. Okay, so that's how PES data works. Pretty easy to interpret once you kind of understand the peaks. All right, so let's go back to the workbook now, and then we're going to look at some practice problems. So to look at the practice problems we're doing, if you want it on your Chromebook, you can click on this, but I'll have it up here. I believe that we did number 1 last time, but just for practice, let's have you guys try number 1. Don't look back at your notes. See if you guys can do number 1 and write a brief explanation why you chose your answer. Try number 1 without looking back at your notes. So you got your PES diagram right here. What element is represented by this spectrum? So take about a minute to do that and write a brief blurb about why you chose that answer. All right, so hopefully this isn't too bad, guys. Let's take a look at the spectrum. So let's first count the peaks. You got 3 peaks, so this is going to be the 1s, this is 2s, and this is going to be 2p. Okay, so let's look at the heights. We know that 1s and 2s are going to be the same. If they are the same, that means they both have 2 electrons, right? So it's 1s2, 2s2. If you look at each of the peaks, there it looks like 2 lines represents 1 electron. So there are 2 electrons here, right? 1 electron, 2 electron. Same thing here. And so if we count the 2p, this is 1 electron, 2 electrons, 3 electrons. So it'll be 2p3. Okay. Now, to finish this up, we're going to look at the periodic table, and we just look for the element that is 2p3. So we got 2p1, 2, and 3. So your answer will be nitrogen. Okay. And then for your explanation, something along the lines of, hey, we got 3 peaks, so we know that it's 2p. And then just based on the peak height, I know it's 2p3 for the last one, and so it's nitrogen. Something along those lines, real quick. All right, any questions on number 1? Okay. All right, so that's an easier problem, just identifying what elements it is. We're going to look at, a more difficult problem now. We're going to look at number 2, and I want to give you guys about 2 minutes to read this and kind of digest it. See if you guys can, first of all, interpret the question, what it's asking you, and see if you guys can choose the right answer. So see if you can do number 2 on your own. After that, I'll go over it and just give you the explanation of the answer. Okay, take about 2 minutes, try number 2. All right, so before we talk about the answer, let's interpret the question first because that's pretty important. So the question is asking, which of these following descriptions best explains first the relative positioning, so basically where the peaks are, that has to do with the x-axis. And if you guys remember, the x-axis has to do with how tightly the electrons are held. Okay, so that's the binding energy. So that's the first thing we are looking at, the binding energy. And also the intensity of the peak. Intensity is basically how many electrons. So number of electrons, which has to do with peak height. Okay, so the answer has to talk about both the binding energy and about the height of the peak. okay, which we know has to do with number of electrons. And then it tells us that you are looking at the 2s peak for these two elements. And if you look right here, you got lithium and you have beryllium. So both of these are talking about 2s. And what we're doing is we're comparing where they are, what their binding energy is, and also how many electrons there are. So let's start by looking at the two peaks. What is the first thing that you notice about the difference between these peaks?
Lithium is easier to remove.
It's easier to remove, right? So lithium is more to the right. So lithium has a lower bonding energy. So that's the first thing you should notice. Lithium has a lower binding energy. Okay, another way you could think of that is beryllium has a greater binding energy to the 2s electrons. All right, what's the other thing that you notice? Yeah, one's taller. Beryllium has a taller peak for 2s, which makes sense because if you look at the electron configuration, lithium is 1s2, 2s1, and then beryllium is 1s2, 2s2. And so we should expect a double the size peak for beryllium, and that's what we see. So we can see that beryllium has a taller peak, taller 2s peak. Great. So those are the two observations that we can make, and now we can just look at the answers and see if they make sense. So the answer is going to be A. I'll just let you guys know off the bat. The answer is A because first, it has a greater nuclear charge, which we know is true, right? Lithium has 3 protons. Beryllium has 4 protons, right? And so there are 4 protons, more positive energy, pulling the electrons in. We're still looking at the 2s, so it's the same energy level, and so beryllium is going to hold the 2s electrons more because it has more protons. And we also see that the answer says there are more electrons in the 2s orbital, which we said is true. Okay, now let's go through the other answers and talk about why they don't work. Okay, let's look at B. It says beryllium electrons experience greater electron-electron repulsions than lithium electrons. Well, this is true in the sense that beryllium has 4 electrons and lithium has 3. But if this was the correct answer, what should we expect from the peaks? If beryllium has more repulsion, if there's more repulsion, is it easier or harder to take out? It's easier. That means that if this was correct, beryllium's peak should be more to the right than lithium's. This answer is basically saying beryllium's electrons should be easier to take out because there is more repulsion. So that's why this answer can't work. It contradicts what we see in the data. Let's look at C. C, it says lithium has a greater pull from the nucleus on the 2s, so they are harder to remove. We know this isn't true because lithium has 3 protons and beryllium has 4. So this is just incorrect theoretically and in the chart. And then lastly, lithium has greater electron shielding by the 1s orbital, so the 2s electrons are easier to remove. This isn't true because both lithium and beryllium has a 1s shell, and they both have 2 electrons in each of them, so they should have the same amount of shielding. So that is incorrect. So A is the correct answer. Okay. So you guys can kind of see how PES is pretty easy to interpret, but especially with multiple choice, there's a lot more options, so it gets kind of tricky as you think about it. All right, let's do 3. Now, if this chart is kind of hard to see, I recommend just pulling it up on your Chromebook so it's easier for you to look at. But I'm going to give you guys 3 minutes because there's a lot more words here to try number 3. Okay, you're comparing 2 spectra. One's for phosphorus, one's for sulfur. See if you guys can answer this question. Okay, so this question is a little bit tricky because there are 2 answers that are kind of correct, but you're looking for the better answer. Okay, so we'll talk about that. But basically, you're comparing the PES for phosphorus and sulfur. And there's 2 things they want you to think about. So first of all, it's asking why is the 2p peak for S further to the left? So if you take a look at sulfur, if you look at 2p, you're going to notice that it's more to the left right here, right? So it's harder to remove electrons from 2p. But why is the 3p further to the right? So if you take a look right here, 3p, you can't really tell by the actual peak location, but if you look at the numbers, this is 1.06 and this is 1.0. Okay, so that's what you are looking at. So I'm gonna give you guys the answer, and then we'll talk about why. The answer is A again. Okay, the answer is A. Okay, so let's talk about why it's A. So first, again, this is a little tricky because every single one of the options, the first statement is true. Okay, so S does have a greater effective nuclear charge than P because it has more protons. B has the same starting one, so that. S does have a greater number of electrons than P. That's also true. And same thing for D. So this problem is a little tricky because every single answer starts with the correct statement. It's just the follow-up that might be either incorrect or not the best answer. If we take a look at A, it says the 3p subshell in S has greater electron repulsions than P. Well, this statement is true because if you look at phosphorus, in the 3p subshell, it's 3p3, and for sulfur, it's 3p4. So there are more electrons in sulfur, so we're going to expect more repulsion in sulfur's 3p. So this answer is true. Okay, and that's the reasoning why. Okay, now let's go to B. B starts with the correct statement, but the second statement is incorrect because it says, and the 3p subshell is more heavily shielded in S than in sulfur than in P. Well, if you take a look at, if you think about shielding, these are the outside electrons, right? If you look, they have the same number of electrons in the inner shells. And so this answer is incorrect because that second statement is not true. Okay, so the second statement in B is not true. Okay, so we look at C, and C is actually the other answer that is true, but it's not the best answer. So it says, since S has a greater number of electrons than P, the third energy level is further from the nucleus in sulfur than in P. So technically it is true that it has a greater number, and we would assume if you have more electrons, they're going to push each other away, right? However, we are not talking about the total number of electrons here. We're talking about just the ones in 3p. And so although this statement is true, it's not the best answer. It's not the best explanation. So A is a better answer than C, and that's the reason that doesn't work. No, not the tables. Yeah. All right, and then for D, it says it starts with the correct statement, and then it says the Coulombic attraction of the electron cloud and the nucleus is greater than in S than in P. This is basically talking about the attraction between the nucleus and the electrons, which we're looking at sulfur. Sulfur has 16 protons and 16 electrons. Phosphorus has 15 and 15. And so this statement is true as well, but it's not the best explanation of why this specific peak is shifted. And so that's why it's not going to be this one. So C and D, they are technically true, but it's just not the best explanation for the specific question that it's asking. It's asking about the 2p peak locations and the 3p peak locations. And that's why you want to look at an answer that talks about specifically the peaks that the question is asking. So A is going to be your answer. All right, so one last one. We're going to look at this one right here. I'll give you guys about 2 minutes to try number 4. We'll talk about it, and then we'll move on and finish up the unit. Alrighty, guys, let's talk. So this question was actually kind of seeing if you're paying attention and you're reading the question carefully. So if we take a look at Na and K, the question is asking us about this spectra. We're comparing the two. However, we're specifically talking about 3s. Okay, now, why is this important? If you guys take a look at Na, Na's electron configuration is going to be Ne, and then it's 3s1, right? Okay, now, if we talk about potassium's electron configuration, let's go from neon. How many electrons are in potassium's 3s subshell? If you look at the periodic table, potassium, 2. Potassium's right here. So to get to potassium, you need to fill up the 3s subshell. We also need to fill up 3p, and then we go to 4s. So potassium is 3s2, 3p6, 4s1. So a lot of people, when they look at this question, they think about potassium and sodium's valence shell. So they start comparing these two together. But the question is saying you're comparing 3s. And so you are looking at these two, the 3s for these two elements. So let's take a look, because this is going to help us figure out our answer. If you look at the peak for potassium, right, it's way to the left, right? And what that means is it's much harder to remove the electrons from potassium's 3s than sodium's 3s. And the reason why, if we think about it, it's going to be the binding energy to the nucleus, right? And so your answer, again, is going to be A. Okay, triple A. Okay, and it's because potassium has 19 protons and sodium has 11 protons. Okay? We can actually answer number 5 as well. If you take a look at the peaks, right? This was also a giveaway. If you look at the peak height, what do you notice about the peak heights? They're not similar. Potassium's double, and it's because potassium's 3s is full. And so that's actually going to be the answer right here. For number 5, we didn't say to do it, but it's going to be D for this one right here. Oh wait, sorry, C. I'm looking at it incorrectly. Na only has 1 electron in the 3s, but potassium has 2 of them. All right, so the last part of the unit is the easiest part. We're going to look at what we call the types of elements. And there are 3 types of elements on the periodic table. They're called metals, nonmetals, and metalloids. Okay, there are 3 different types of elements: metals, nonmetals, metalloids. Now, you guys don't need to memorize a lot of stuff from here. This is just kind of basic information you just need to be somewhat familiar with the terminology, because we might see it, but don't feel obligated to memorize all this stuff word for word, because it's not that important. Okay, so if you look at your periodic table, I have a little diagram of it right here. Everything in yellow are going to be the metals. So if you guys take a look, the vast majority of the periodic table is metals. So left side, middle, bottom. That's the easy way to think about it. Okay, we'll talk about the properties in a second. The other section that I think is easiest to remember are the nonmetals. Nonmetal is just the top right, or pretty much the right side. The only exception is hydrogen. Hydrogen's up here on the top left, but hydrogen is a nonmetal. And then metalloids are in this middle. They make this little staircase area right here in the middle. Honestly, the ones that are important to remember are boron and silicon. If you remember those 2 are nonmetals, you should be fine. Or sorry, metalloids, then you should be fine. All right, let's talk about some of the properties of metals and nonmetals and metalloids. So I'm not going to go through all of these. This is in your reading that everybody I know is keeping up with. The key thing to remember, though, are these 2 right here. Metals, they want to lose electrons and become cations. Okay, so metals are pretty much all the time going to become cations. Okay. So metals want to be cations. That's the most important chemical thing. And that's why if you look at the most common ions that we've been looking at, everybody on the left is +1, +2, right? If you look at the transition metals, all the examples you get, it's +3, +4. You don't have any negatives in the left and the middle of the periodic table. They're all positive. Okay, nonmetals are the opposite. They're not like metals. And so they like to gain electrons and they become anions. So if you look at the MCI pattern on the right side of the periodic table, it's -4, -3, -2, -1, so on and so forth. The exception to this rule right here are the noble gases. Obviously, we've talked about this. And noble gases, they do not want to gain or lose. They are nonmetals, but they don't want to become ions. Okay. And then metalloids, they are kind of they're kind of have the properties of both metals and nonmetals. So you don't need to be that familiar with them. Just know that boron and silicon are metalloids, and you should be fine. Okay. Alright, so I'm not going to spend too much time talking about this because I'll be honest with you, it's not that important. As long as you are somewhat familiar with the terminology, you should be fine. Okay, so real quick, I'm going to have you guys try 815. So based on what we just talked about, I want you guys to use your regular periodic table. Don't look at the one that I have up there. See if you guys can use a regular periodic table and just your general knowledge of where they are. See if you guys can just figure out what type of element these four are. Okay, so are they metal, non-metal, metalloids? Just real quick, I'll give you a minute. Okay, so if we take a look at the periodic table, we can just kind of guesstimate what they are based on where they are. First one that we looked at was tungsten. It's in the middle. That's a metal. Okay, uranium down here. It's in the bottom. It's a metal. Krypton, far right. It's a non-metal. Germanium's the one that's a little bit tricky. This is a metalloid because it's in this little staircase diagonal area. Okay, that's it. So just know that pattern. Left, middle, bottom are metals. Right side is non-metals, and hydrogen is a non-metal. And this middle part right here, that staircase, that's the metalloids. Okay. All right, let's finish up. So the reason why it's important to know what the different types of elements are is because that determines the types of compounds and molecules that we make. So we briefly talked about this, I think, in the first unit that we did together. But there are three different types of bonds. The first are called ionic. And ionic is where typically it's made out of a metal and non-metal. Okay, this is where a positive cation and a negative anion combine together and they make an ionic bond. Now, the key thing to know about an ionic bond, so if you guys want to jot this down somewhere, in a ionic bond, okay, the cations, so the cations, they give an electron to the anion, okay? So for example, if we drew the Lewis structure for Na, Na is the 1 valence electron, Cl is 7 valence electrons, Na wants to lose 1, Cl wants to gain 1, and so Na gives its electron to Cl, that makes it positive, that makes it negative, they see that opposites attract, and then they get married and they combine together, okay? I know, it's beautiful, that's why we call it chemistry. Okay. So ionic electrons are transferred from the cation to the anion. Okay. Okay. Let's go to covalent. Covalent is the one we're gonna actually learn how to draw these later. But covalent is interesting because instead of electrons being given to one of them, atoms, they start to share electrons with one another. And typically, this is going to be a non-metal and a non-metal combining together. Okay, so it's going to be the elements on the right side of the periodic table. Okay, that's where electrons are shared. And we're going to spend a good amount of time learning how to draw these covalent compounds, how they get shared. But that's next unit, I think. I don't really remember. I think it's next unit. Okay, covalent is where electrons are shared. So big difference. Ionic, electrons are given, and covalent, electrons are shared. All right, and then the last type of bond that we're not going to look at too much are called metallic bonds, and it's where metals and metals combine together. We're not going to be looking at this too in detail, but just so that you guys know how it works. In a metallic bond or metallic compound, you have these positive nuclei, and these electrons are being shared freely. So these electrons, they can move around. We call this the electron sea. And it's because electrons from one atom can move freely between all the different atoms that are in the metallic bond. Okay? All right, and those are the 3 different types of chemical bonds. And congratulations, guys, that is Unit 8.
All of them. All of them.
Probably just.
I searched 4 on it. I'm right D. No, I'm not right. I'm right D. She's gonna be like drawing all over it.
That's such a bad. You gotta have that. Like,
Dude, my phone case is my mom. I sent it to my mom and she put exclamation mark. And then I'll show that.
so, do you do the quest for the Kalos starters yet?
Hmm?
Have you been doing the quest for the Kalos starters?
No. I'm just trying to rip through the story.
It's like not that long.
I'm rank B right now. I'm getting there. I have a kid, so it slows down my progress. He's basically holding me back. He's slowing down my Hey, the amount of games I played before and after kid has shrunk significantly.
I would imagine.
Yeah. When he was first born, it was so easy. It doesn't sit.
Wait, did I?
Wait, oh, that was me.
Literally, all my dad does is sit and play his game.
Yeah, because you're grown now, and you don't need your diaper changed.
I know.
You're not, hopefully, not trying to kill yourself all the time.
Hopefully not.
Dude, my kid, he's been trying to freaking stick the fork in the outlet. He has like a strange obsession with that.
I like that. That's good. Probably makes you feel great when you set him down.
Oh yeah. I've had to hit him a couple times because he's done bad things like that. And he tried to stab me with a fork, so I hit him for that too. But I hit him the most when he was biting. He was biting me a lot.
I'm gonna repost it photos just so you can zoom in on the emoji.
We're all equally as